And so, yes, I'm trying to actually tell you the story of the search of the torus. So I will start by thanking my closest collaborators. Thanks to them, we have been able to get to this point. And they come from very different countries and very different institutes, as you can see. Many of them are here, actually, and will be giving talks. Okay, so I would like to first, because I see many people here works with stars and exoplanets and things like that, define what is an AGN. I find this a very good, very objective definition. A galaxy containing a massive accreting black hole, where the mass has to be larger than 10 to the 5 solar masses, and with an Eddington ratio exceeding 10 to the minus 5. They are very energetic sources. They are emitting all over the electromagnetic spectrum, as you can see here. We have radio loud and radio quiet, AGNs, and in the infrared, which you can see the torus, the accretion disk, in the UV and optical, and we have also emission in the X-rays. And okay, so why are they important? Well, because in the cosmological sense and in terms of galaxy evolution, they actually might be changing how are galaxies evolving. So maybe their feedback can explain the missing dwarf and massive galaxies in this plot here, where we see the K-band luminosity function of galaxies. And okay, so at some point, we knew about many kinds of these galaxies, and there were two in specific where we could put them all. The type 1 that presented broad emission lines, and the type 2 that had narrow near infrared and optical UV emission lines. And well, at some point, Antonucci, Uri, and Padovani in 1993 and 1995 proposed this theory of the AGN unification, where they will say they are actually the same kind. It's just that we are looking at them from a different point of view. So if we look from here, we see a type 1, we look from up here, and if we look from here, we see a type 2. But the main point of this theory was actually the existence of this structure, which they call the torus. And it has to be optically thick, geometrically thick, and it has to be made of dust, because then the dust is actually trapping all the UV photons coming from the accretion disk, and we're emitting them in infrared wavelengths. So what was the evidence that we had for this theory to really make sense? Well, we had alignment of optical polarization, position angles with the radio structures in type 1 objects. We had also an anti-alignment in the case of the type 2 objects. And we had also a general alignment of ionization currents with the radio structure. And finally, we had an infrared excess and deep silicate features that were pointing at the presence of a lot of dust somewhere there. Okay, so the idea of the torus started in a very simple, very naive way, with a very smooth, very simple, very geometric, symmetric, nice torus. The function that it needed to do was to obscure the central engine and to collimate the narrow line region, maybe to fit the black hole. And this idea started evolving because, well, as we worked more and more and we observed more AGNs, we discovered, okay, this is not enough, because if we had a smooth torus, it will flatten out very, very quickly. So, and then some observations were pointing at the fact that things were moving fast. So sometimes we had extra emission, sometimes it was gone in very short time lapses. So then the idea of the clumpy torus came, where we could keep the geometrical thickness, and we could explain certain effects of the variation of the X-rays. But other observations were telling us, okay, but we still need the smooth part. So this evolved to a two-phase medium torus. And I will keep on telling you more about the evolution, but as I tell you more about what we were finding. So now I will talk about NGC 1068. It's a very popular Cypher 2 galaxy. It's at 14.4 megaparsecs. It's one of the closest ones, one of the most studied ones, and it's very famous because it's said to be a hidden Seifert 1. So in polarized light, Antonici and Miller in 1985 found that it looked like a Seifert 1. It's also a Barrett spiral, and the mass of the black hole is about 1.5 times 10 to the 7 solar masses. It's a really quiet galaxy. It has a very small radio jet. And okay, we are studying it with Matisse. If you want to learn a lot more about Matisse, listen to Bruno Lopez's talk tomorrow. So I will skip any details on Matisse. And well, MGC 1068 was known to have a water maser right at the center. And they were related to this radio source at 5 gigahertz. And well, the velocities are very high, which means the stuff has to be in a disk, very, very close to something that is really massive. The black hole mass was calculated to be 10 to the 7 solar masses. And well, these are just characteristics of how the radio continuum was related to the masers. And it was explained to be thermal free emission from an X-ray heated corona or from winds from the molecular disk. So we are very, very close to the black hole. Now, the predecessor of Matisse, MIRA, found this source in the very, I think this was commissioning data, so there were not so many UV points. And they found this compact here, not well resolved, and more or less resolved source here, not very large, of about 4 parsecs, and where the component in the center will have hot dust of 800 Kelvin, and the larger component will have dust to 320 Kelvin. So these pointed at the fact that, okay, it might be there. This was telling us, okay, might be there. So further research with MIRA, with more UV points, gave way to this other 3 Gaussian model, where they found again a compact source, more extended source, and a very extended source. And they gave temperatures of 300 Kelvin, 700 Kelvin, and 300 Kelvin to these sources, respectively. Now, this was using AT and UT data. The other results were made with UT data only. And it was the position angles that we see were actually close to the position angles that we see in the water masers. So this was also very nice. Further studies of AGNs with MIRA found that actually many AGNs, so in this case 7 of 23 AGNs that were studied, had this extended emission, and that it was usually towards the polar regions. So, and if you want to hear about the Matisse results of Cercinos, you need to listen to Jacob's talk, and of ISO 323G77 to James' talk. I think they're both today later. And okay, so now the torus models have to evolve once again to explain that emission to the polar regions. So now we think that there might be dusty winds that are radiation driven. And okay, so now ALMA has observed MGC 1068 several times. This is one of the most important results because they found this circumnuclear disk, but you can see it's like 300 parsecs away from the well, that's actually the diameter, but it's not centered. The AGN is not centered. But okay, they found that there is clumpiness and that there must have been recent star forming activity. Now, as we zoom in, actually here, as you can see, it's like this is like 7 parsecs. They found this source, and they found that it had strong non-synchronous motions and enhanced turbulence, but it also had signs of being counter-rotating with respect to the water masers, which is really intriguing. And the size that they gave to these molecular gas torus was 7 to 10 parsecs. So again, we're getting there, but we are still not knowing yet what's going on with the dust. So until very recently, Gravity Collaboration 2019 made this beautiful image reconstruction of NGC 1068. And they interpreted these very pink sources as this dust sublimation region. And this was because the distance, the radius seemed to be very good, like the right size for silicate grains or graphite grains. And also because when they made a study of the CDs, they found that the temperature could be 1,500 Kelvin, which is the sublimation temperature of silicate grains. And so they put the black hole right here, right in the middle of these sources. And this is the way they related it to the masers. As we heard before, they didn't have astrometry, so this was made thinking a lot of what makes sense and how can we explain things. But yes, it is not completely established. And so, okay, here you can also see the VLBI source, the radio source, and how they related it to it. We have to compare two things that have a similar resolution. In this case, these ALMA observations found this really nice extended, like with a butterfly shape continuum at 256 gigahertz. And this is the way it relates to the VLBA source, and the water masers are also around here. And the most intriguing aspect of this publication is that, again, they found that the outer disk is counter-rotating with respect to the inner disk, which will be the one defined by the masers. It's only like about 1 parsec. So yes, so now we can look at the MATISSE data. This is commissioning data from 2018. So you can see here that we're resolving the source. You can see that there's a lot of asymmetry. We have closure phases that are varying a lot all over the L and M bands. And this is how we started studying NGC 1068, because we knew a little bit of how it looked like in the N band. So we focused first in the L and M bands. And this is what we got with a simple two Gaussian model. This is at 3.4 microns, but actually we found that all over the L and M bands, we were finding the same two sources. And this was very nice, but we didn't exactly know what was happening. And the distances and the temperatures that we were getting with the ST feeds didn't make a lot of sense, because they seem to be independent sources. So at some point we started thinking maybe we got two black holes, but luckily enough, we got more observations in November 2019. And so now we had a total of 5 snapshots. These are UV plane. The little crosses are observations where we lost 1 telescope. So it's like 4 and a bit observations. And this was very nice because we found out that we could do actually image reconstruction. And these are the image reconstructions that we got for L, M, and N bands. And for the N band, we used the MATISSE data too. And these are not to scale. I just want you to see that there is a lot of asymmetry, again, that we have very complex sources. At least in the L and M bands, we have similar sources, which is really nice. The N band data seems to be very different, and it's very extended, actually. And we can see also that this second source, it's prevalent in the L and M bands. Now, we were actually able to prove that that source is real. And we did this by doing some narrow band image reconstruction. And we see that when we take the medians of all these, the source is there. The source is there all throughout the L and M bands. So this was very nice. Now, how do we cross-identify this with the gravity results? Well, again, we don't have astrometry, but we can take a guess. And this is how we thought, okay, looks like this might work out. So in general, we can say that the brightest part of the L band and M band are actually covering these brightest spots of the gravity sources. And okay, so for our image reconstructions, we actually double-checked. We double-checked in many steps, many things. And so we tried with MIRA, airbase, with point source, overfitting models, and Gaussian models. And well, if you're picky, you might say they don't look so alike. But what we did was actually to define areas of interest and to do the photometry all over, like an aperture photometry. And then we compared the fluxes that we were getting with the different methods. And we found that they were very similar. Only for the second source down here, we were getting different things. And that's something that we still now we don't know how to explain very well. So this is how we did it. We get, so in the case of the Gaussian modeling, after 2 Gaussians, things were crashing really badly. So we have to guide ourselves through the image reconstructions. We took the image reconstruction, we put Gaussians, and we took this as a first guess, and then we fitted the models, and we were getting good fits, actually. For L and MS, we used 7 Gaussians. For N-band, we used only 3 Gaussians. We used the minimum number of Gaussians such that we will get an acceptable fit. And for that, we used 10 degrees in closure phase and 0.01, I think, in scored visibility. And so, okay, after having the models for all the bands, all the wavelengths that we wanted, we put these areas, these ellipses, on where we were interested. We tried to gather all the flux, and we tried to use apertures that were large enough for the resolution in the end band to still work. And so we could integrate all the bands at the same time to create SEDs. So now when we have the SED, we can actually learn about the dust properties, the dust temperatures, the dust composition, and optical depths. So we did this, we tried different kinds of dust. Our main result is that we needed amorphous olivines with sizes of 0.1 microns. And actually, we found that we might need some carbon grains. We tried with, with ISM dust, with iron, with pyroxenes, with many things. And this was something that was giving us a good fit. Now, what's going on with the K-band flux? We actually had a problem that it was we took the paper, gravity paper, and the K-band flux was too high compared to what we were doing. So we actually had to talk to the gravity team and ask them, okay, what are you reporting? What did you do? What exactly is happening? What's happening with the fluxes? And they gave us a very good hint on, okay, this is the percentage of the flux that you need to use if you only want to take the flux related to these sources. So this is something very important when you compare and when you make an SED, you have to use the flux that it's inside the same area. Otherwise, things don't make sense. And okay, so actually, it's plotted here, and it's not perfect, but it's not so bad. Now, the one unexpected result was that the temperature that we found, so if you remember, this is the gravity sources were, they reported 1,500 Kelvin, the temperature of the dust, and we found a very low temperature of 560 to 700 Kelvin. So this was really unexpected, because if we put the black hole here, then we need a very high temperature. So, okay, we did a lot of double checking. One of the things that we did was that we compared our photometry with other previous observations in the L and M bands, and we found that it fitted nicely. So we were happy about that. We continued with the SED fitting. You can see here that for the apertures, we have very, very deep silicate features. And for some of them, you don't have almost any K-band flux or very little L and M band fluxes. So this is nice to see, because it seems to be that the cross identification that we made was working well. And we discovered that actually, because we don't have astrometry, we had to guess how to overlap all those images. And we decided to do, okay, we're gonna take the brightest point of every image and we're just gonna overlap brightest points. That's how we worked. And we found that if we were shifting 3 milliarc seconds these images, then the SEDs will not, we could not fit them at all. So we trust that what we did was the best. And okay, here's an example of what happens if we use standard ISM dust. you can see it's the green stuff that is here. The 8-micron flux is never fitted, is never reached. And this happens for every SED in every ellipse. So this is very important. Very well. So now we have, for all the areas that we chose, we have temperatures, and we can actually make a temperature map of our AGN. And we find that for the extended emission, we get very low temperatures of 150 Kelvin. But for the what we call the northern complex, which is formed by these 5 greenish ellipses, we found that actually, well, as I told you before, E1 had a very low temperature, but all the other ones had very high temperatures. We put 1,500 Kelvin as the upper limit because of the sublimation temperature of silicates. We also found that the southern extension, which is this ellipse here, the pink one, has also a very high temperature. So this was also very unexpected. With respect to the extinction, we noticed that there were very large variations in very small scales, and that the opacities were increasing systematically from the center to the southwest. So as I'm showing with this arrow, this was telling us that there is a layer of dust with a density gradient towards the southwest. And okay, so now when we compare to other observations that have a similar resolution, we started comparing to ALMA, and we found we did a cross correlation with the image. But I mean, from the first moment that we saw both images side by side, we noticed that they had almost the same morphology. We find these like X-shape, they called it X-shape, I call it butterfly shape. And we found that they were very, very similar. And this is very unexpected because we are comparing emission from free a very hot electron gas versus cool dust. Just the temperatures are like 200 Kelvin. Furthermore, when we compare to the VLBA 22 gigahertz continuum, these are new observations, we find that again we have a morphological similarity, and this was also very unexpected for the same reasons. And here we can see how the water masers are lying very nicely to the sources. Okay, so all this, we put together all these, the map of temperatures, the opacities, and the cross correlations with the ALMA sources and with the VLBA and the water masers. The VLBA and water masers and ALMA, they all have astrometry. And so we could actually pin down the position of the black hole, and we think it's here. And so our conclusion is, okay, we are finding the torus. We are finding the layers of the hot dust and the colder dust that are making up and are hiding the accretion disk and the central engine. So we are very happy about this result. We were able to publish it in Nature earlier this year. But yes, there are some remaining issues. Now, I don't know, how long do I have? 4 minutes. Okay, I want to talk to you very quickly about more work that we're doing with 1068 and with MATISSE data. Okay, so in the squared visibilities, in some baselines, we saw that we had a little bump here at around 3.5 microns. So we started wondering, okay, what is that? And this is actually the reason why we started testing the carbon dust together with the olivines, because we thought, okay, if those are hydrocarbons, or there has to be carbon, because it could be also nanodiamonds, but you have to have the carbon somewhere. So we started seeing more carefully what was this about. So we fitted a single black body, and we used the same kind of dust that we had concluded that we had in the other paper. And we actually were doing this for the different correlated fluxes. We found 4 different kinds of features that you can see here. And we started comparing them with different features that have been seen in other sources. And unfortunately, or fortunately maybe, only for the type 1, so this red one that it's peaking at 3.46 microns, we found similarities. And here are some of the comparisons that we made. So we find similarities with protoplanetary nebulas, with YSOs, with post-AGB stars, and even with ANOVA, V128 equal. And this is very exciting because it's a way to link the center of a galaxy with galactic sources. And so these features in the other sources are explained as superhydrogenation or having aliphatic groups, but it's not, there is no conclusion on that. But okay, the other thing that we have in our photometry is, well, this feature, which is aliphatic hydrocarbons, has been observed in some AGNs in NGC 1068. This is an 8-meter spectrum, and it is related to the diffuse interstellar medium. Thank you. And so we were wondering, why do we have so many kinds of features and how can we explain them? So for the type 1, we were a little bit happy with the identifications that we made, but for the other types, we weren't. So we started thinking, what if this feature, because actually the wavelengths are not the same, it's actually eating up the other feature. And so we started making some experiments where, so you can see here the type 1 in red, and we are adding extinction by this feature in this way. And we start getting to a flat profile, like in the type 2. And if we continue, we actually get to a profile where it peaks at 3.62 microns, like our type 3 feature. And if you continue, you get actually a completely flat profile where that only has a deep absorption feature here around 3.35 microns, which is what we call the type 4 feature. And well, this is really cool because we are playing around with emission and absorption, and we can explain in that way some of the features that we have. But our main result with this analysis is that actually the variations in the absorption and the emission on both, it's taking place on sub-parsec scales. And so, okay, this is the way we can explain it. We need to have layers of dust with different temperatures. Some of them get directly the UV photons, and some of them don't. And so as you have more or less absorption here by the colder clouds, then you start getting the different types of features. And so, okay, that's all. Here I'm showing you the all the LM and M bands image reconstructions. They are overlapping, and the plane that we think that is the main plane of the torus, the equatorial plane of the torus. And my conclusions are Matisse is super cool. Use the LM and M bands if you can, the 3 of them. And well, yes, we think that the torus that we find agrees with what we were expecting with respect to the winds and the classical torus. And we need to improve the torus models now with respect to these new findings, because there are many open questions left. And yes, we are working on it, but it's a long way still. And listen to Romain Petrov's talk on Friday.
Thank you very much. No questions in the chat yet, in the room. Please.
So does your observation tell us about whether the torus is clumpy or not?
Our observations?
Yes.
Yes, well, based on actually the latest, this part, we need lumps, because otherwise you cannot have the interplay between absorption and emission.
Thank you.
Makoto?
Yeah, I've got one quick question. If you get a map and the flux, then what is the emissivity of that, or the map of the emissivity? Do you actually have a map of emissivity of that mid-infrared flux? I mean, emissivity means that the surface brightness in units of Planck function. I mean, if you have emissivity of quite close to 1 here in the mini infrared, then you can actually show that the gas is actually quite optically thick in the optical and the UV.
So in the thermal maps, we actually do have, I don't have, it's a boring table, so I didn't put it here, but we do find the optical depth for all these ellipses. And we can see actually how it is dominating here, the extinction is dominating here. I don't know if that's what you were asking for.
Yeah, the large extinction. Well, but I mean, I'm just talking about the continuum emission. So you've got the color temperature, and then you've got the flux or the surface brightness distribution, so that you can actually get the number for the emissivity of that all mid-infrared emitting material here. Well, maybe we should go offline. Thank you.